Hi, my name is Austin Harless, and today I'm going to share with you how we could have prevented the Pascagoula gas plant explosion and fire that occurred on June 27th, 2016. And here's how I'm going to do it. First, we'll discuss a little bit about what the plant does. Then I'll describe the accident in detail, including the events that happened before and after the explosion. Next, we'll discuss some of the vulnerabilities of the equipment that was used at the plant and the problems that led to its catastrophic failure. And finally, I'll give my recommendations to prevent another incident like this from occurring. So, the Pascagoula gas plant was constructed in 1998 with Amoco holding 60% interest and Shell holding 40% interest. In 1998, BP bought out Amoco, and by mid-1999, Enterprise purchased all of Shell's interest. And it stayed this way until March 2016, whenever Enterprise Products purchased BP's interest in the plant and gained operatorship. So Pascagoula gas plant operates by pipelines connected to deep water wells, which provide raw natural gas to the plant. Then the plant separates into three products: a natural gas condensate, a lighter natural gas, and heavier hydrocarbons known as natural gas liquids. And the plant does this by using a cryogenic separation, which utilizes brazed aluminum heat exchangers, which are a very common piece of equipment found in the 500 gas processes, cryogenic separations across the country. Now that you know the basics about the Pascagoula gas plant, let's go into detail about some of the events that occurred prior to the explosion. So the Destin pipeline provides raw natural gas to Pascagoula, and then two products leave through the Destin pipeline, and a third leaves through the Tri-States pipeline. The Tri-States pipeline takes natural gas liquids and processes them further. On the night of June 27th, Pascagoula gas plant had two operators running. One of them was in the blast-resistant control room, and the other one was in and out of the control room as needed. At 10:30 p.m., the Tri-States requested a curtailment in flow due to issues they were having downstream of Pascagoula. And then 20 minutes later, a complete stop of flow was requested due to a lightning strike that had shut down operations. Due to the limited storage capacity at Pascagoula gas plant, they needed to completely stop their natural gas liquid production. Part of the normal shutdown procedure is to manually light a burner on a hot oil furnace to add more heat to the demethanizer column. The resulting heat allows more natural gas liquids to vaporize and become part of the gas streams, rather than sent to the bottoms as natural gas liquids. A surveillance video shows the operator arriving at the furnace at 11 p.m. and leaving a minute later. After returning to the control room, the board operator provided tutoring on the written shutdown procedure. The operators continued their shutdown with no alarms or warnings until a loud boom was heard. The initial explosion occurred at 11:22 p.m., which was captured by surveillance footage and coincided with various instrument failures and temperature spikes. After the initial explosion, the outside operator left the control room to observe the unit and immediately radioed back to shutdown. There's two emergency shutdowns procedures at the Pascagoula gas plant. ESD 1000 doesn't depressurize the plant, but shuts down all liquid and gas flows into and from the plant, while also shutting down some additional equipment. ESD 9900 goes a step further and vents the gas in a predetermined sequence by sending most of it to the flares and releasing the rest to the atmosphere. The board operator initialized ESD 1000 about a minute after the explosion and initialized ESD 9900 only 23 seconds later. Within 2 minutes, the operator contacted the plant operations supervisor, who then called 911 and headed to the plant to assume the role of incident commander. After speaking with the plant supervisor, the board operator noticed a vent on top of the B-train methanizer had caught on fire. This vent wasn't designed to catch fire, so the operator decided to reset the ESD 9900 system at 11:33 p.m. After seeing the flames go out, the operator reinitialized the ESD 9900 system at 11:45. The Pascagoula Fire Department was first to arrive on the scene at 11:30 p.m., with 3 volunteer fire departments arriving shortly after. Emergency responders, in conjunction with PG-Peer personnel, decided the best course of action would be to let the fire burn itself out and utilize cooling equipment where feasible. The emergency responders also decided that no residential population would be in harm, so they decided against an evacuation. The fire began to diminish around midnight, and emergency responders returned at 2:30 a.m. to set up fire monitors. The fire burned out at 6 p.m. The explosion and fire caused Enterprise to incur $17.5 million of expenses, and the plant was shut down for 6 months. Now that we've gone over the events that occurred on June 27th, let's talk about the root cause of this accident: thermal fatigue in the brazed aluminum heat exchanger. In general, the brazed aluminum heat exchanger is a device that allows heat transfer from a hot process stream to a cold one. The BAHX does this by a series of alternating hot and cold layers separated by parting sheets. Inside these layers, there are corrugated fins and sidebars to seal the fluid inside. These layers are collectively called the core of the BAHX, and the outer layers are sealed with cap sheets, which are thicker than the parting sheets. The fins connection to the cap and parting sheets are critical to the structural integrity of the brazed aluminum heat exchanger. When the layers are pressurized, the fins act as a truss and counteract the fluid forces on the cap and parting sheets. The benefits of choosing a brazed aluminum heat exchanger are highly efficient heat transfer and a compact design that can accommodate many different process streams. However, some of the disadvantages include exposure to fluctuating thermal stresses and plugging of small passages. When a BAHX is exposed to fluctuating thermal stresses over an extended period of time, this can lead to thermal fatigue, which will be one of the main causes of this accident. The post-incident examination of this exchanger revealed very clear service-related thermal fatigue at several locations. The exchanger was already experiencing thermal fatigue in September 2015. In September 2015, HETSCO, a third-party service provider, repaired interpass leaks in the outermost layers of the exchanger. There was a leak in layer 98 and layer 2, as you can see in the figure. So they decided to weld the inlet and outlet of layers 99, 98, 2, and 1 shut, and leave layers 97 and 3 open to the process. The leaks could have possibly been coming from either of the adjacent layers, but it was treated as if the problem was not in layers 97 or 3, which can be seen in the figure. This crucial engineering decision is the first of many service-related failures that caused the accident on June 27th to occur. A good engineering practice when performing guesswork like the engineers responsible for this decision is to check your work. HETSCO welders drilled holes into the sidebars of the layers to allow gases produced during welding to exit and so they could perform leak tests. However, no documentation confirms a leak test was performed. The failure to perform a leak test is the second reason that the catastrophic failure of the brazed aluminum heat exchanger was able to occur. Sometime between the repair of the brazed aluminum heat exchanger and 205 days of operation before the incident, the vent holes were blocked on the layers that had been welded closed. Without open vent holes, the blocked layers had no means to relieve pressure if a hydrocarbon leaks into them through a thermal fatigue-induced crack. On the night of the incident, when the unit was warmed up, the increase in temperature of the exchanger caused by hydrocarbons to enter the block layers and become trapped. This caused a buildup of pressure and led to the eventual catastrophic rupture. The failure to leave vent holes to prevent pressure buildup is the third reason the catastrophic rupture was able to occur. The blocked ventilation holes inside the block layers would not have caused the problem by themselves. For a catastrophic rupture to occur, hydrocarbons must have a way to enter these layers and create the pressure inside them. The parting sheet that separates one of the block layers 98 and one of the non-block layers shown showed evidence of thermal fatigue cracks and can be seen in the figure below. Assuming this crack extended through the layer, it would have allowed fluids from the active pass to the blocked off layers. This crack could have been present at the time of the 2015 repair, since no evidence is shown that they performed a leak test, or the crack could have developed in the 205 days of operation after this repair. The crack in the parting sheet adjacent to the block layers is the fourth and final step necessary to create the catastrophic rupture that happened on June 27th. First, I'll give my recommendations for servicing brazed aluminum heat exchangers. Recommendation number 1 is that leakage testing should be mandatory for all brazed aluminum heat exchangers that go under service. Recommendation number 2 is to assure that proper ventilation is installed in the block layers to allow pressure relief. Recommendation number 3 is to require manual audits each time a brazed aluminum heat exchanger is serviced to assure proper engineering decisions have been made and the equipment is up to spec. Now I'll give my recommendations for predicting thermal fatigue. Recommendation number 1 is to use operational data to optimize the use of brazed aluminum heat exchangers to minimize exposure to thermal stresses. Recommendation number 2 is to use predictive stress modeling to observe how shutdowns affect the life of the heat exchanger. Recommendation number 3 is to use this data to create new ratings for maximum and minimum operating conditions if old ones are not considered safe anymore. Thank you for listening to my Pascagoula gas plant fire and explosion investigation. Have a great rest of your day. Thank you.